Good morning, everybody. Today our lesson will be on implicit differentiation. Before we begin, we're just going to go back and review a few things. Remember, differentiate means find the derivative. We have a bunch of different notation we can use. You guys are most familiar with that, f prime of x. Okay, but we know that that notation just means find the derivative. We can also just say y prime, and we're going to start now to use this notation, dy dx. Basically, this just means derivative of y with respect to x. It's just different words that mean the same thing. And the other notation, I just want to remind you, this is just our general way of saying the derivative of a function. Okay, sometimes we use this notation when we're like kind of representing rules. The notation we use depends on the type of problem you're solving. And you'll discover in calculus, you're really going to start to use different notation for different types of problems. Let's just go backwards for 1 second. Explicit differentiation. So explicit differentiation is the differentiation that you guys are used to when we take the derivative of a function that's already in the form of y equals. So we just really never use the word explicit. We usually just call it differentiation. For example, if I have y equals 4x cubed minus 7x squared plus 6, you all would know the derivative would just be 12x squared minus 14x. If you have s of t equals negative 16t squared plus 20t, you'd probably go s prime of t equals negative 32t plus 20. Okay. And you're all used to doing with that, doing it, and you're very comfortable with it. Sometimes our equations won't be so nice. So if I ask you to differentiate something like this, x squared plus y squared equals 4, this might be a little bit hard for you. Okay, I want to remind you, we're dealing with a circle, right? This is just a circle that has a radius of 2. Okay, so when we deal with circles or things like this, we could actually take this and we could solve this, right? We want to get our equation as y equals. So we would bring the x squared over to the other side and take the square root of both sides, and we wind up getting two equations, y equals plus or minus 4 minus x squared. And if you recall from earlier in the year, the positive version is the top part of the curve, and the negative version makes the picture of the bottom part of the curve. Okay, so that's stuff you should sort of remember. All right, so now what does this mean to us when we're taking the derivative? Well, we're going to wind up with two rules. One rule will give us the slopes of the top part of the curve, and the other rule will give us the slopes as we move around the bottom part of the curve. So what we have to do is we have to break this up. And I'm going to rewrite it right away with my fraction power. Okay, so we're really going to be taking the derivative of two functions to get the rules as we move around this circle. So my y prime is going to be 1/2 derivative of the outside times the derivative of the inside. And if I clean this guy up, y prime becomes, my 2's are going to cancel, negative x over 4 minus x squared to the 1/2 power. Let's see what happens on this side. Y prime equals negative 1/2 derivative of the inside, and I wind up getting, my 2's again are going to cancel the negative, so this time I get x over 4 minus x squared to the 1/2 power. So I have two rules. Okay. One gives me the rates of change around the outside, the top of the curve. The other is for the bottom. So let's just really quickly, okay, let's just really quickly find the slope of the tangent at the point 1 radical 3. So that would be probably somewhere around here. Okay, we want the slope of that tangent line. Okay, that's basically what we're doing. So what we're going to do is we're on the top part of the curve, so we're going to plug into this rule. So y prime would be negative x negative 1 over 4 minus negative 1 squared to the 1/2 power. So y prime is going to be negative 1 over 4 minus 1. That's going to be 3, so that would be radical 3. So the slope of our tangent line at that given point would be negative 1 over radical 3. Okay. So let's just kind of talk about this. Is there a better way to do these types of problems? Yes, there is. So basically, we just need to know some vocabulary. So we say that the equation x squared plus y squared equals 4 is defined implicitly. This means not in the form y equals. So if we want to find the derivative, we have to solve it for y, and we saw that was rather confusing. So in calculus, we have a way to deal with this, and that's called implicit differentiation, and we're going to use this when it's too difficult or not possible. Sometimes you won't even be able to solve for y. So when you see things like this, x's and y's together, you're going to use implicit differentiation. Super easy. You take the derivative of each term. Okay, if the term has an x in it, you put dx next to it. If the term has a y in it, you put dy dx next to it. This is if you're taking the derivative of that term. And you will understand what I mean in just a second. And lastly, you're going to solve for dy dx. Okay, so let's go back to our original example and see how we can apply this. X squared plus y squared equals 4. I don't want to solve for y first. I want to use implicit differentiation. So I go term by term. Take the derivative of this term, 2x. Since this derivative had an x in it, I'm going to write dx dx. It's going to look weird for a second, but we're going to talk about it. Move on to the next term. 2y dy dx equals the derivative of 4 is 0. Now dx dx is simply just a 1, so that cancels. And you have 2x plus 2y dy dx is equal to 0. Now to get dy dx by itself, this is what we want to keep. Okay. We're going to bring that 2x over, so we can just subtract that over. And then the last step would be to divide, because this is really attached by multiplication. So our last step is we're going to take dy dx, and that's going to be equal to negative 2x over 2y, or once we simplify that, dy dx is equal to negative x over y. And that would be the answer. Okay. Now I want to remind you, this is really the derivative. This is just a rule to find the slope of the tangent line. This time, though, our rule uses both x and y. And that's something different than we're used to. But let's look to see how easy it can be. So find the slope of the tangent line at the given point. So we're going to now, instead of going back and having to, pick which one to use, we're just going to use this rule. Oh, and let me show you some notation here, because this might be helpful for next year. We want to evaluate the derivative at the point 1 radical 3. It's nice to be able to use this notation. Okay, now remember, The derivative is negative x over y. Negative x over y. My y value. And let's just see if that matches the answer we got. And it sure does. Okay, so we got the same answer. Okay. I think this method is a whole lot easier. Okay, so now what I want to do is, now that we kind of feel comfortable doing this, we're just going to work through a handful of examples, and then we'll be done. So differentiate. My x's and y's are attached together. Okay, so rather than solve for y, I'm just going to use implicit differentiation. Go term by term. 2x, dx, dx. Some teachers don't write the dx, dx. I like to, so I apologize if that bothers you. Dx, dx cancels. Okay, and now I know I'm going to be moving the 2x over, so I have 8y dy dx equals negative 2x. Now I'm going to divide negative 2x over 8y. And the last thing you could do is simplify this if you want. I will tell you, in calc, you really don't have to simplify your answers, but sometimes it just makes it easier if you're moving on with a problem. Okay, so we have dy dx equals negative x over 4y. Let's take a look at number 2. X times y equals 1. Now I've got a product rule. Okay, so I'm going to want to apply my product rule. Any rule we already know. Okay, now we can incorporate that with implicit differentiation. So my product rule is the first term times the derivative of the second, which is the derivative of y is just 1. But since I took the derivative of a term with the y in it, I'm going to write dy dx. Plus the second function times the derivative of the first, dx dx, right? I'm taking the derivative of a something that has an x in it, equals 0. My dx's cancel. Now I want to get dy dx by itself, so I'm going to move the y over using subtraction. And then I'm going to divide by that x. And there's the rule for the derivative. 2 more to go, and we will be done for the day. Once again, I have myself a product rule. X times y squared equals 1. The first term, we're going to leave that alone, times the derivative of the second, 2y dy dx, plus the second term, y squared, times the derivative of the first. The derivative of x is just 1, so I'm just going to write dx dx equals 0. Dx dx cancels out to a 1, so you just don't worry about it. Now I have 2 times x times y dy dx, and I'm going to move this y squared over. And my last step would be to divide through. I have negative y squared over 2xy. And now I can simplify. This y is going to cancel. Dy dx is going to equal negative y over 2x. Okay. 1 more to go, and then we'll be set for the day. X cubed plus x squared y squared minus 2y equals 0. Term by term. 3x squared. I took the derivative of a term of an x, so I write dx dx. Now I've got a product rule. Plus the first term times the derivative of the second, plus the second term times the derivative of the first, minus 2 dy dx equals the derivative of 0 is just 0. Now here's where things might get a little bit crazy. So if you kind of look here, I've got a dy dx here and a dy dx here. And this term are going to be moved over to the other side. So a lot of times what I'll do is I'll take this piece and this piece and kind of combine them. X squared, actually I'm going to move my multiplier out front because I hate it the way it is. 2x squared y minus 2, and those are in front of the dy dx. It's kind of like the binomial there. And I'm going to subtract over negative 3x squared. That took care of that. And I'm going to subtract over a 2xy squared. All I did was rearrange it so it looks kind of like we're used to seeing things in math. And now the last step here, to get dy dx by itself, you divide through by this whole entire binomial that stays together. So in the numerator, that stays the same, and my denominator becomes that. And remember, you could, if you wanted to, you could try to simplify if you can. I really don't think there's any way to simplify this one, so I'm just going to leave it alone. Okay, so now we got through the examples that I wanted to get through today. All I want to do is kind of remind you really quickly, even though we're using a different method to find the derivative, the answer still means the same thing. It's a rule we can use to find the slope of the tangent line at a specific point. Just this time, we're going to plug x's and y's into our rule to get the derivative. Okay, thank you. See you soon.